So in section 2.4, it's our last section of chapter 2. And as I had mentioned in section 2.3, this will only really consist of one theorem, but we do introduce a lemma, so technically it's two theorems. But it's basically just that one theorem that's a punchline, and we're pretty much done with this section and with this chapter. And we will be moving on to continuity next, chapter 3. So let's just begin. We're going to introduce a definition first because we do have the word monotone. So here, let f map d to r. The function f is said to be increasing, or in parentheses decreasing, if and only if for all x, y in D with x less than or equal to y, then f of x is less than or equal to f of y. And in the case of decreasing, f of x is greater than or equal to f of y. And if f is either increasing or decreasing, then f is said to be monotone. Right, so because it's a weak inequality, a function, for example, if it looks something like this, a constant function, that's both increasing and decreasing, right? Because f of x at this x and at this y, or I should say the y here, this other y, this point is less than or equal to this other point. And again, the f of x is also greater than or equal to f of y, right? So intuitively, increasing kind of just means not decreasing at any point. And decreasing basically means not increasing at any point. So if we take a look at the picture, the step function, what do we have? Well, we have, this is an increasing function, right? At all the points, this holds true. As long as x is less than or equal to y, this inequality holds true. So this is an increasing function. Now, what if I were to define for alpha less than x less than beta, define u of x to be the infimum of f of y such that x is less than y, and L of x to be the supremum of f of x, f of y such that y is less than x. What if I were to define that? So for example, let's say this here, let's say, oh my gosh, this one here is our alpha, and this here is our beta. Let's not include this point. So u of x is the infimum of f of y such that x is less than y. Well, if x is right here, let's say this point is x, or it's up here, x, then the infimum would basically, well, all these points are constant, so the infimum is this value here. This is u of x. The supremum, because it's constant, is also, it's on the left side now because here y is less than x, but it is constant as well, so that value is also L of x. But for a function that looks something like this, and let's say x is right here, then on the right hand side, we look at L of x. No, sorry. On the right hand side, we look at u of x. U of x is an infimum, so the infimum value of the functions greater than zero, of the values greater than zero, is right next to it, right here. So this is for u. Same thing for L. The supremum of all those values would be somewhere there because it's the value is less than x. So they're pretty much be together. But what if we extend it, for example, down here? What if we extended this like, give me a second to erase here. What if x was this point here in green? X is this, and beta is this point, this is alpha. Now in this case, I'm going to label u of x as blue. So to the greater than x, what is the infimum of those values? Well, the infimum of the values to the right of x is, well, because it's constant, it's just here or here, any point those. This is the infimum, so this is u of x. And what is L of x? Well, the ones to the left of x, so it's these values here. So this would be L of x, right? And now they're not really together, right? Or u of x and L of x aren't really that close. So u of x minus L of x, the way we're defining them like this is because this kind of measure, or actually this measures the jump at x of a point, right? So u of x minus L of x measures the jump of f at x. And we'll see that f has a limit at x naught if and only if the difference between u of x and L of x is 0. So, oh, there you go. It wasn't responding. So the lemma says that let f have domain a closed interval alpha to beta mapped to R, and let f be increasing. We're going to let u of x and L of x be defined as the previous slide, where x is in the open interval alpha to beta. Then f has a limit at x naught if and only if u is equal to L, so here. And in this case, the limit of f of x at that point x naught will be the same value as u of x naught and L of x naught. So it's kind of what I just said, but now we're actually going to be proving it formally. And this is the lemma for the theorem we're going to see in the next slide. This lemma is probably the longest theorem we've seen thus far, if I'm not mistaken. So let's get to it. And just one more thing I need to point out. Oh, here it is. Let me erase this up here. Because it is if and only if, that's why we get kind of like a longer proof. It is biconditional, so we will have to prove both directions. So first, suppose f has a limit at x naught called a. Choose epsilon greater than 0. And again, we're assuming this first thing because we have to assume it here and prove one direction. Well then, because it does have a limit at x naught for the delta greater than x minus x naught, the difference between f of x and the limit point a is less than epsilon. Well, because x naught is in alpha, the open interval alpha beta, well then we can find points x and y such that we can wedge them in x and y here between x minus delta and x naught, and between x naught and x plus delta, right? So we can find x and y such that we can wedge those points in somewhere in between there. So by definition of L and U, and the fact that f is increasing, what can we say? Well, that the values a minus epsilon is less than f of x, which is less than or equal to L of x naught. Right, we're kind of like wedging those points in. We're just getting the image of the points up here, and that is less than or equal to f of x naught. That's less than or equal to the u of x naught, which is less than or equal to f of y, which is less than a plus epsilon. So I should color code this to kind of avoid confusion here. This we got from this red. This we got from this. And now these, I suppose I can use yellow. Actually, you can't really see yellow too well. So let me use dark blue. This and this comes from the definition of L and U. So that's how we get all these values. Well, therefore, it's in U and L are in our epsilon neighborhood, right? So the difference is less than 2 times epsilon for epsilon greater than 0. And because we can make epsilon arbitrarily small, well, U of x naught is equal to L of x naught. Thus proving that L of x naught is equal to f of x naught, which is equal to U of x naught. Moreover, more information. Moreover, U is in that neighborhood of the limit. Therefore, U is the limit, right? Because again, we can make epsilon arbitrarily small. Therefore, our one direction holds. We just proved one direction. So therefore, this is true. And again, I'm just going to erase here to kind of not confuse us anymore, as we're going to prove the next direction. Now we're going to suppose that U of x naught is equal to L of x naught. And as observed, we have this here. Right, and that's just because of how U and L are defined. Well, we have that U of x naught is equal to f of x naught, which is equal to L of x naught. So what do we need to show? Well, we need to show that f does indeed have a limit at x naught, and that limit is what we'd expect it to be, right? The limit as x approaches x naught of f of x is equal to f of x naught. So choose epsilon greater than 0. Now L minus L of x naught minus epsilon isn't an upper bound of this. Why is that? Well, because it's to the left, right, of x naught. So it can't be an upper bound of it. And similarly, U of x naught plus epsilon isn't a lower bound for this because, well, it can't be, it's to the right of x naught, right? It's not to the left of it. So it can't be a lower bound for it either. Well, then they're real numbers, y1 and y2, such that we can wedge them into the interval, and such that L of x naught minus epsilon is less than f of y1, and also such that f of y2 is less than U of x naught plus epsilon. So similar to what we were doing above, right? We're wedging in numbers, and their image is also like kind of wedged in there. This is what we're wedging, the y1 and y2, so that this holds similar to the reasoning we just used above. Well, now we're going to let the minimum be either the one that or the one that's less. We're going to let delta be the minimum of x naught minus y, y1, and y2 minus x naught. So basically, we're going to let delta be the the difference that's less between these 2 points and between these 2 points. Whatever difference is less, we're going to let that be the minimum. Sorry. We're going to let delta be the minimum of whatever difference is less. Well, now, if delta is greater than x minus x naught, then this should hold. So f of x naught minus epsilon is equal to L of x naught minus epsilon, which is less than f of y1, less than or equal to f of x, less than or equal to f of x, f of y2, which is less than u of x naught plus epsilon. Meaning what? Well, again, because they are in that epsilon neighborhood, we have f of x minus f of x naught. That difference is less than epsilon. Therefore, f has that limit at x naught, and that limit is f of x naught. So again, we're using a lot of wedging to kind of show, hey, well, things are arbitrarily close. For these two directions, we're using that wedging, which works because, again, we're using epsilon here in this proof, and epsilon can get arbitrarily small. So things we wedge in also get arbitrarily close to either a limit we're trying to show or values we're trying to show, u and L, that those are basically the same because their difference gets arbitrarily small. So some is quite complicated. The theorem itself shouldn't be too hard to understand, right? As I showed last slide, the difference of u and L should be the same if we expect there to be a limit at a point, which is what this theorem proved, or this lemma proved. Which kind of, we kind of move forward to our, but this theorem isn't really as complicated. There is something I will have to explain which kind of confused me the first time around that I read it a few years ago. So first we're going to let f be monotone. And again, it maps the closed interval alpha beta to R. Then D is going to be all the points x in the open interval alpha beta where f does not have a limit. I'm going to show that that set D is countable, meaning there are only countable many x's where f doesn't have a limit. And if f has a limit at x naught in alpha beta, then that limit is f of x naught as x goes to x naught. Okay, so our proof, assume f is increasing. And again, let D be all those points of x where f does not have a limit. Well, by the lemma of the previous slide, x is in D if and only if the difference between u and L is not 0. And because it's increasing, u of x minus L of x is greater than 0. So if the function were decreasing, right, we would have that u of x minus L of x would be less than 0. But in this case, well, it's increasing, so the difference of u of x minus L of x is greater than 0. Well, now here's a kind of bit confusing part. We're going to let d of n be x such that u of x is greater than L of x. Sorry, u of x minus L of x is greater than 1 over n. So for example, maybe I should show the next one, and then this will be a bit clearer. So For example, or down here, D4 is all the points x such that the difference between u of x and L of x is greater than 1/4. Right, so for example, if we had an x where a jump, I'm going to draw a function here. Let's say at this point down here, x, the difference between u of x, and L of x, this distance here is greater, not less than, greater than 1/4. Well, then x would be a member of D4. Similarly, for D5, right, D6, so on and so forth, also D3, D2, and D1. That's what that set is doing. So clearly, D, all the sets, all the x's such that f doesn't have a limit of that point, well, is the union of all the sets Dn. Right? Because if x is in D, well then x has to belong to some Dn. So this is going to be true if we show that D of n is finite. Why will that be true? I guess I don't have it here, but that will be true because union of countable sets is a countable union of countable sets is countable. So suppose, actually, before I even read that, I will have to write down here again. So let me erase this. Suppose x1 to xr is in D. So all these elements, x's, all these x's are in Dn, meaning they don't, f doesn't have a limit at those points. We're going to set them up in an order. We're going to put them in an order, right? So if we have the closed interval alpha, the open interval should be alpha, beta. All those points that don't have a limit, we're going to set them up in order. X5, X6. I'm going to leave that there because, and I mean, it doesn't just go up to X6, it goes all the way to XR. But now we're going to choose Z1 to ZR plus 1 such that we wedge these values in here. So this is Z1. Between these 2 points, we're going to put Z2, Z3, so on and so forth, all the way to 5, Z6, all the way to ZR plus 1, so Z7. That's what that line is saying. We're going to wedge those values in. Now, for each f of z1, so f of, actually I should keep my colors consistent. F of z1, or in this case, f of zi, is less than or equal to L of x1, or sorry, xi. And why? Well, because remember, z1 is to the left of x1. So the supremum of all the values, let me draw a picture so this is clear. Let's say here is our x1 because that's the first point where we have a jump. Well, this here, this point in orange would be L of x1. And then let's say alpha was over here. Beta was, I don't know, somewhere over here. So what is this saying? This inequality here is saying that Z1 is wedged somewhere in this section, right? This green section here. Well, because this function is increasing, that whatever value we have, either this point, this point, this point, this, all the points, well, that's definitely less than or equal to this orange point, L of xi, or in this case, L of x1. Does that make sense? So f of zi is less than or equal to L of xi. Similarly, u of xi is less than f of zi plus 1. So concrete example here would be f of z1 is less than or equal to f of x1, which is less than or equal to f of z2. Right, so we're dealing with these 3 points down here for this concrete example. And again, we get that because this function is increasing. So next, we get that f of zi plus 1 minus f of zi. Well, that's greater than u of xi minus L of xi. And that's greater than 1 over n because of how we defined the sets d sub n, sorry. So now, f of beta minus f of alpha, so taking the 2 endpoints wherever they are, that difference is equal to f of beta minus all the little jumps added together. Right, we're going to add all the little jumps from z1 to z2, plus the jump from z2 to z3, plus the jump from z3 to z4, so on and so forth. We're going to add all those jumps. So that's why that difference is equal to all the little jumps and it's not just the little jumps, but it's also just as the function is increasing. So that's what this is doing. This here, I should say, accounts for all our little jumps and also for when the function is increasing. It's another way to rewrite f of beta minus f of alpha, which is basically just saying how much the function increased from one endpoint to the other in the interval. And that is greater than r because we have our many x's, and then they're all greater than 1 over n, greater than or equal, no, sorry, greater than 1 over n. So that's why this is greater than or equal to all the r's times 1 over n. And since this is definitely a real number, right? A function can only increase so much in a closed interval. It's a fixed real number. Well then, let me erase here. R, there's only so many of those, and that has to be less than n times f of beta minus f of alpha. So each dn only has finitely many n, right? It can't have infinitely many because, again, this is a fixed real number such that this inequality has to hold. So therefore, dn is finite for each n. And again, if we take the countable union of countably many countable sets, we get that D is countable, thus proving our theorem. So again, this lemma, this theorem may be a bit complicated, maybe the most involved so far, but visuals are always helpful. Kind of try to prove this on your own and see where you get stuck and then peek at the theorem. see what's necessary, what conditions, and you can see how this proof really works. That should be it for section 2.4. We're going to be looking at continuity next on section 3.1. I believe, well, we obviously state the definition, and we see how we actually define continuity, not just maybe in calculus you learned as, drawing a function without lifting your pencil from the paper. Next section will actually be defining it rigorously.